Okay, so as Joachim said, in the last year there's been really two major advances that have made NGSolve more usable and easier usable with MPI again. So those are, on the one hand, our own AMG or algebraic multigrid package is now on GitHub publicly available. That works currently for scalar H1 as well as 2 or 3D linear elasticity problems, and it's quite efficient to about 10,000 cores or so. On the other hand, which I want to focus on more, is our PETSc interface, which is something that's been developed in the last couple of months, or in the last 2 or 3 months or so. So it's still in a very early stage. So if anyone is interested in that kind of thing, we are very thankful for any kind of feedback. And if you want to get into this and make sure that it's also going to develop in a direction that's maybe useful to you, this is the time to try it out. So for those of you who don't know PETSc already, PETSc is a general collection of linear algebra of different solvers, Krylov-space solvers, nonlinear solvers, which have been proven to be very, very scalable, and it's just one integrated interface and one gets access to a whole lot of different things. And on top of this core package of linear and nonlinear solvers, there's also the tau library for optimization, and then there is an eigenvalue solver, an eigenvalue library. But those are two things I haven't looked into yet. But I suppose if it's interesting for a lot of people, the groundwork for that has also been done. So if you want to go to the PETSc interface, you can just go type in NGSolve on GitHub and there should be a link there. For the MPI workshop tomorrow, for those who are interested in, we will also be using the PETSc interface in some places. But it's also installed on the VirtualBox we will upload at some point today. So let's first show what this AMG package can do. So I saw Joachim's talk before about the model templates, and I decided to really quickly incorporate this. And he was saying that it's not really set up with MPI yet properly, but I thought this is everything already so nice, and it's probably not a lot of work to really quickly hack into that. And I don't need to explain what's actually going on because you've all seen it half an hour ago. So this is again the linear elasticity problem. And I will not, so when I execute this cell, it takes about 1 minute or so. And the only thing I have to do here is to replace this preconditioner inside this model with, well, NGS AMG, 3D elasticity AMG, and then I put on some logging information. And I didn't import it, right? Yes. Yes, of course, I did not set up the model. Thank you. So I think this takes about 30 seconds or so. Yes. So it has solved this equation in so 7 seconds, and of that, almost all of the time was actually, if we take out the bilinear and the linear forms and we assemble them and time that, it's almost all of the time is actually in assembly. So that's on the one hand pretty quick, and on the other hand, this is also, as I said, something I've had running up to 10,000 cores. So we have some options to scale stuff up, and you also saw that picture already. But that's really very standard NGSolve. We just did a precondition, and the only thing that's changed here is that we now have a new flag. So what I think is more interested is the PETSc interface. So PETSc also gives lots of options to assemble already distributed sparse matrices, but that's not the direction we decided to take it. We were thinking more along the line of to do everything default NGSolve, to assemble your matrix, and then if you're in a case where you want to use PETSc, you just convert it to PETSc and you use a precondition or a solver from there. And additionally, you always have the option to convert, if there is some specific solver in NGSolve you want to use, you can use that solver within PETSc. And on it the other way around, if there is just a solver you want to take out of PETSc, you can do that too, and do your CG or Newton or something on NGSolve side. And one thing I would also like to mention here is that there is a complete Python interface from PETSc side, but they are doing things very differently. So we are trying to provide just objects that are sort of parallels to NGSolve objects, but in the background to PETSc stuff. And the PETSc interface is doing the exact same for PETSc. So that's a very C-like interface, and it doesn't mesh so very well. So that's a very different approach. So we start with a unit cube. So I set the edge relatively fine here, so this will take a little bit to mesh. Okay, so the first step when we want to define a KSP, a Krylov-based problem, is to convert the matrix. So we just import this NGS PETSc interface, and then we construct the PETSc matrix. So because PETSc doesn't really have a native support for Dirichlet boundary data, the thing I'm doing right now is just to only convert the the rows and columns that belong to the freedofs. So when you do in NGSolve a dot inverse, you also get something similar where you have the inverse operator only on the freedofs. And when you convert something to PETSc, that's already the case for the forwards operator. So that's something I'm doing currently. I'm not really set on this yet, whether this is the way to go. And then the thing which I found very nice when I started with PETSc, and which I think many people probably think the same thing, is that so inside PETSc there is this database of options, which are like, I don't know, probably 1,500 or so string flags, which you can provide on the command line somewhere. And we can all the time add to this library or to this database and do a lot of customization of what PETSc does in the background just by handing these strings. So for example, here we are creating a KSP object, so a Krylov-based problem object. We give it the matrix it's supposed to operate on, and then we give it a tag, so it's my super awesome linear solver. This is just to identify this thing within PETSc, because what we are setting here are in the PETSc options, for example, the KSP type is CG. But these options just get ported over with this prefix, so not every KSP you construct after this also thinks it's supposed to take these exact options. So then we say relative tolerance 10 to the power of -8, and then we give it, as a precondition, it should use GAMG. This is the AMG solver, which is implemented in PETSc itself. And I also gave it these 3 flags here. And we unfortunately have to go over to the, so sorry. And the KSP is implemented as a base matrix, so we can just solve the problem by applying it just like an inverse operator. And that way it can also be incorporated in the normal operator algebra. So if we go here to the terminal, unfortunately, I couldn't get this to pipe to the Jupyter session. So one thing I gave was KSP monitor. So it prints during the computation, it prints norm of residuals. And this huge chunk of text here gives you all of the information about the KSP object that was created, because I gave it this KSP view option. So if you are not sure what PETSc does internally, you just hand it this flag, and then it lists you exactly what is the object you're working with. But for the most part, this is just a huge wall of text, especially if you're using one of the multigrid solvers. So this KSP object is really what's at the very heart of PETSc, and sort of in the next shell around this KSP are the nonlinear solvers. These are generally called SNES, so scalable nonlinear equation solvers. What we are going to do here, yesterday in the afternoon we had this nonlinear session, and there we had this neo-hook example, which we can now fortunately do with the model template. So the entire setup is just 15 lines. Because our primary concern is right now is not how exactly to set up this problem, but how to solve it. So during a nonlinear solve, you get a whole bunch of places where you have to linearize your matrix and where you have to assemble a linearization. And then you have to solve a linear problem there. And in order to be flexible here, I built in an additional option in this place, which so you have the choice. When you assemble linearization, do you convert this matrix to PETSc, or do you keep it only on NGSolve side and just wrap it in a PETSc wrapper? So the actual linear algebra is done on NGSolve side. For example, if you have a matrix in NGSolve and also a solver in NGSolve, and you just want to use one of the fancy nonlinear algorithms from PETSc, you can use this in flat mode, so without doing any conversions, and basically do the entire linear algebra in NGSolve. The only overhead you have then is you sometimes have to copy vectors back and forth, and the reason for that you even have to do any vector copying is that I cancel out all of the Dirichlet-offs, which is one of the reasons why I am not really completely set on this idea yet. And beside this, it's pretty much the same. So we construct a PETSc SNES object, we give it a bilinear form, we tell it that in this case, because we want to construct the precondition on PETSc side, we actually have to convert the matrices, and then we give it a couple of PETSc options. And a couple of options. So this is again the same thing. So all of these KSP options configure the linear solver that's in the background, and the SNES options themselves configure this nonlinear solver. And so here, this is the first test. I put in preconditional type Jacobi, and we see, well, the KSP object or the KSP solvers take quite a few number of iterations, even for a relatively small elasticity problem. And if I make a bit of a finer mesh, it diverges. So the default maximum number of iterations is 1,000, and it couldn't converge within that. So we can try to do this one better, and instead of Jacobi, we use GMG. Again, this is the default algebraic multigrid solver from PETSc. And we see how that works out. And the linear solvers are better, but they are still quite a few iterations. And the reason for that is that elasticity is one of those problems where you can't really do a very efficient black box solver. You need some additional information. In this case, in order to be efficient for elasticity problems, that was the wrong order. What the solver needs is information about how the rigid body modes are exactly, about the coefficient vectors of the rigid body modes. Because those produce no energy, so when you build coarse levels, you have to take care of them. So this is something, and this, because we need a vector here, this is something you cannot do only via the command string. So, but because this is a very common theme, so here we make the rigid body modes vectors, and then, well, from the SNES, we get the KSP, so that's the linear solver context, and from that we get the matrix out. So this gives us a PETSc matrix. And then we call set near null space, and we give it the rigid body modes. This is one of those standard PETSc functions. You can attach a near null space to a matrix, and then the solver will try its best to incorporate that information. And then let's try it again. And we see we now converge in like 10 iterations or 12 compared to 35. And this is also a version which can scale basically ad infinitum. As I also mentioned very shortly, we can also go the other way around and just use PETSc for preconditioners, and we can do our own solve nonlinear problem from one of the I tutorials. And instead of computing this inverse matrix here, we convert the linearized matrix to a PETSc matrix. Again, the rigid body modes, we will need them. We set the near null space, and then instead of an exact inverse, we're doing a KSP, and we are again using GMG. But this time the Newton solver itself is on NGSolve side. And yes, that works again. So I think for the linear solves, most of I think really a good portion of PETSc features are already working in the interface. On the nonlinear is pretty bare bones. And as I said, these extension libraries I haven't even touched yet. And there is also one thing which is a very great feature of PETSc, which are field splits. So those are preconditioners for block systems, which I haven't gotten to run efficiently yet. But I think it's, for many cases, already quite a nice tool, especially if you just want to compute a reference solution and maybe compare, and even if you just want to do a reference computation in order to know in which regime of performance you are. But there are also many more features to go. So if this is something you're interested in, and if you maybe realize that there is some specific thing that really should be in that interface, then please tell me about it. Thank you.